In Chapter 3, we will cover elementary quantum physics. Much of the physics of materials requires the physics of atoms or elementary particles such as an electron. In several aspects, these elementary particles do not behave classically and requires us to use quantum mechanics. In this section, we will describe aspects of light which are best described using the concept of light as a photon. Recall that visible white light is actually composed of an entire spectrum of light containing all the colors from violet to red. Also recall that the physics of light is well described by wave mechanics, where the wavelength of light varies from around 400 nanometers for purple light to 700 nanometers for red light. Visible light is actually just a small member of the electromagnetic spectrum, where beyond the wavelength of red light lies infrared, microwave, and radio waves, while below the wavelength of violet lies ultraviolet, X-rays, and gamma rays. When we say light is an electromagnetic wave, we mean that light can be described as a traveling wave of oscillating electric and magnetic fields, where this oscillation happens in both space and time. Waves are best described mathematically using sine or cosine functions. For example, the electric field in red can be described as a function of position x and time t using sine kx minus omega t. This equation describes a wave moving in the positive x direction, where E naught is the maximum value or amplitude of the electric field along the y direction. The parameter k in the equation is known as the wave number and describes how spread out the wave is in the x direction. We often characterize this with a wavelength, where the wavelength describes the distance between one complete oscillation of the electromagnetic wave. Thus, when x increases from 0 to 1 wavelength, we expect that kx should increase by 2 pi. This gives us the relationship for wavelength lambda equals 2 pi over the wave number k. In a similar manner, the parameter omega describes how fast the wave is oscillating in time. Here, omega represents the angular frequency, such that when omega times t equals 2 pi, the wave has gone through a complete oscillation in time. The frequency of the oscillation measured in hertz, or cycles per second, is then omega over 2 pi. The speed of a wave written in this form, also known as the phase velocity, is given by omega over k. In this case, since we're talking about light as a wave, we're talking about the speed of light given the symbol c. Using the relationship between omega and frequency, as well as wavelength and wave number, we also get perhaps the more familiar form that speed equals frequency times wavelength. Also remember that this equation describes the electric field and that the intensity of light is proportional to the square of this field. Mathematically then, to find the intensity of this wave, we will square it, and so we'll do this also in quantum mechanics. A key characteristic of waves is that they diffract. Consider, for example, the double slit experiment for light. Here we have our light going through a single slit to make a point source that then illuminates a double slit. The light emanating from these two slits then shines onto a screen where, if the light is in phase from both slits, we have constructive interference that gives us a bright band, or if the two waves subtract or destructively interfere, it gives us a dark band. Mathematically, the condition for constructive interference is that the path difference between these two light beams must be an integer number of wavelengths. For destructive interference, the path length must be such that the two beams are exactly a half a wavelength apart. These conditions are known as diffraction conditions and really only expected if light is traveling like a wave, and wouldn't be expected if light were traveling like a projectile. In material science, we use diffraction of light in the form of X-rays to characterize crystalline materials. The first clear indication that light doesn't always act as a wave was in the photoelectric effect. In the photoelectric effect, we have a metal cathode and metal anode placed in a vacuum with the idea that any electrons which come off the cathode could then be collected by the anode and their current measured. The kinetic energy of these electrons can also be measured by adjusting the voltage between the cathode and the anode. Now, normally the electrons in the cathode are relatively tightly bound, and very little current flows from the cathode to the anode. However, it was observed that when light is shined onto the cathode, often electrons are ejected and flow to the anode. If light were simply a wave, one might expect that the kinetic energy of these electrons would depend only on the intensity of the light. But instead it was found that it depended more on the frequency of this light rather than the intensity to determine whether electrons would come off at all. For example, in cesium metal, there were no electrons that came off until a critical frequency, and then above this critical frequency, the kinetic energy increased linearly with frequency. Other metals, such as potassium and tungsten, behaved similarly, although they had different cutoff frequencies. The slopes, though, were the same. Experimentally, then, the kinetic energy of these electrons that come off can be modeled with a constant times the frequency of the light minus the cutoff energy. This minimum energy or cutoff energy to produce any electrons at all is known as the work function, and the constant h became known as Planck's constant. This equation can then be interpreted that the kinetic energy of each electron that is measured is due to a burst of energy supplied by the light, or a quantum of energy, minus a work function that depends on the type of metal used for the cathode. We can think of the work function as the potential energy of the electron when it's in the metal with all the ions relative to the vacuum outside the metal. Thus, we can think of the electron as living in this potential well, where the edge of the well is the boundary between the metal and the vacuum. We can then think of the light as providing the energy to lift the electron out of the well and also provide it some extra kinetic energy on its way to the anode. The light interacts with the electron by providing a quantum of energy, where that quantum depends only on the frequency of the light and not on the intensity. The intensity of the light simply increases the number of electrons ejected. Thus, we think of light as a quantum called a photon, where a beam of light contains many quanta of photons heading the same direction, containing the same frequency, and each has a pocket of energy defined by its frequency and Planck's constant. Photons individually interact with matter in a quantized manner, but as we add more photons, the wave nature of the light becomes apparent. Light can also scatter a free electron, as in this example, adding not only energy, but also changing its momentum. In this example, there's also a scattered photon, and this photon has an energy and a momentum itself, which can be calculated using the principles of conservation of energy and conservation of momentum when we think of each of these photons as having an energy and momentum themselves. In this Compton scattering experiment, it was shown not only that the energy of the photon is h times frequency, or h bar omega, where h bar is h divided by 2 pi, but also the photon momentum could be defined where momentum p is h over lambda, lambda being the wavelength, or h bar k, k being the wave number. Thus, although we normally consider light as a wave, when light interacts with elementary particles such as electrons, we should think of light as being made up of photons, where each photon contains an energy determined by its frequency and a momentum also determined by its wavelength or wave number.